Okay, I think we are live now, right? Yeah. So, what we're going to do is talk about the relationship between a and a squared, relating characteristic polynomial, minimal polynomial, and the eigenvalues. Um, Remember that characteristic polynomial includes all the eigenvalues of a matrix in it, and we will also see the relationship between the eigenvalues of a to the eigenvalues of a squared. Remember that the eigenvalue of for every eigenvalue of a, let's call it lambda, the corresponding eigenvalue on a squared will be lambda squared, and we will show the proof for this. And also we will look at a very perplexing entity, which is if I have eigenvalues for a squared, are they always come from eigenvalues of a? I would use the Jordan form and things like this to show that all the eigenvalues of a squared comes from eigenvalues of a. We'll use some similarity in matrices. So this is the what I want to do. So let's start. It will be some questions. So the first question relate the characteristic polynomial. Oh, you don't see. Let's just show you what I'm doing. Okay, now you can see it. Now the first question asks about the relationship between the characteristic polynomial of the matrix A and the bilinear polynomial of the matrix A squared. We know that for a 3-on-3 matrix A, we have a characteristic polynomial which is this one. And if you look on this characteristic polynomial, you will understand that A has 3 eigenvalues. Eigenvalue 1 equals 1, eigenvalue 2 equals 2, and eigenvalue 3 equals 3, because this is a characteristic polynomial. Now the question asks if it's true or not that the minimal polynomial of a squared, not a, is this one, namely t minus 1, t minus 4, t minus 9. Remember that in the characteristic polynomial I have the eigenvalues, but also in the minimal polynomial I have the eigenvalues of the matrix. Namely, this tells me that the eigenvalues of a squared are 1, 4, and 9. Now the question is that right or wrong? Is this really the minimal polynomial of a squared? Let's prove it. So this will be correct. I mean, this is true. The reason is that every eigenvalue of a can be translated to an eigenvalue of a squared, which is lambda squared. Let's show you something. If I have an eigenvalue lambda for a matrix A and an eigenvector v not equal 0, v, by definition, eigenvalue satisfies this equation for eigenvalue lambda, right? This is the definition for eigenvalue AV equals lambda v. This is the definition for an eigenvalue. Now, when we square and looking on a squared v, we can write it as AAV. Now, AV we can write as lambda v, so we are writing here lambda v. Now, this lambda we can take out, is a scalar, so we can write this. Now AV again is lambda v, so we can write this. So we get lambda squared v. So what we get is that a squared v equals lambda squared v. Namely, lambda squared is an eigenvalue of a squared. What we learned is that if we have an eigenvalue lambda of a, so the eigenvalue squared is an eigenvalue of a squared. Okay, this is just this direction, not the opposite. But it's important. So if I have for a eigenvalues 1, 2, 3, what will be the eigenvalues that will come in a squared? 1 squared, which is 1, 2 squared, which is 4, and 3 squared, which is 9. And we don't have any other eigenvalues because the matrix A as a squared are 3 on 3, so they can't have more than 3 eigenvalues. So those are all the eigenvalues of a squared. There cannot be any more, and therefore this is really a characteristic, let's say, at least polynomial of a squared, but because every term is to the power of 1, the characteristic polynomial must divide, the minimal polynomial must divide the characteristic polynomial, so it should have at least any term to the power of 1, so it must be the minimal polynomial because you cannot remove any term. So this is really the minimal polynomial of a squared. You can see here the proof, but this is the idea. The eigenvalues of a are 1, 2, and 3. Now, when we take the minimal polynomial of a, it's still, because every eigenvalue has algebraic multiplicity of 1, it must be also the geometric multiplicity, so the minimum polynomial is this. And when we square the eigenvalues, we're getting this. So those are the eigenvalues of a squared. We don't have more eigenvalues, so this must be the minimum polynomial. So this is true. Now the next statement is, let's see this one, asking about a squared and a. If I have an a squared where the characteristic polynomial of a squared, not a, is this one, can I say that a is diagonalizable? And now, again, a is 3 on 3. If I have 3 different eigenvalues, I can straight away conclude that the matrix is diagonalizable because if I have 3 different eigenvalues and the matrix is 3 over 3, so the algebraic multiplicity will equal a geometric multiplicity, and of course a will be diagonalizable. The question is, what are the eigenvalues of a? Now, think about it. One of the important question here is, are all the eigenvalues of a squared come from a, or there are different eigenvalues that can come from other areas? Namely, all the eigenvalues of a squared came from a or not? All the eigenvalues of a squared derived from lambda, which let's assume it's an eigenvalue of a, or not? So we saw one direction, which is this one, that if I have an eigenvalue of a, the squared eigenvalue is an eigenvalue of a squared. Now, in order to tell you, and if there is any mistake, please tell me, I will show you that this is true. Every eigenvalue of a squared came from an eigenvalue of a, and therefore, because we have 3 different eigenvalues for a squared, because this is the characteristic polynomial, it must be that a has 3 different eigenvalues, and therefore a is diagonalizable. So let's see. In order to this is the a squared with the characteristic polynomial, and those are the eigenvalues. So the eigenvalues of a should be +1 -1, +2 -2, or +3 -3 in order to their square to be what we need. Now, how do I prove to you that all the eigenvalues of a squared came from eigenvalues of a, and not, for example, I won't have things like this for eigenvalues of a, namely 2 eigenvalues 1 and 1, 2. So from this we get 1 and 4, but 3 came from somewhere else. The idea, I think the best idea, come from the diagonalizable form or the Jordan form of a. So a, I don't know, let's not assume that it's diagonalizable, but I can find Jordan form for a. So if I take a Jordan form example for 3 on 3 matrix, you will see that this is example of a matrix. Oh, this is a Jordan form already. So you see that this is a Jordan form. Now, if I square this, I will get to a matrix which is not guaranteed to be Jordan form, even it's not a Jordan form. But look at this matrix. This matrix is a Jordan form, is similar to A by definition. Maybe I wrote it here somewhere. Jordan form is similar to A. So you see the connection. Here it is. So Jordan form is similar to A. Now, similar matrices share the same eigenvalues. Now, if I square this, let's square this, I will get this. Okay, a squared equals p j squared p minus 1. This means that a squared is similar to j squared. Now, j squared doesn't have to be a Jordan form, but Jordan form is a triangular matrix. When you take the square of j that you wrote in the example, when you take the square of a triangular matrix, what happens is that diagonal entries just get squared. So now I see, and it's diagonal matrix, you can see. So if, for example, I have a matrix A, okay, and it's similar to a Jordan form, this. So I know that the eigenvalues of A are 5, because if you look on triangular matrix, the eigenvalues are on the diagonal. And if A is similar to this, so A has the same eigenvalues, so it's 5. Now when I look on the squared, the diagonal just squared and it stays a diagonal. And the diagonal just squared and it stays a triangular matrix, upper triangular in this case. So now the eigenvalues for j squared are 25, which are the squared of the Jordan form of A. It's not a Jordan form anymore, but it's still a triangular matrix, because if you take a triangular matrix and square it, you stay with a triangular matrix. So A is similar to a matrix that is triangular, and the diagonal are just the squared of the diagonals of the Jordan form of A. So A squared is similar to a matrix that its eigenvalues are squared of the eigenvalues of A. And those are all the eigenvalues for A squared. So all the eigenvalues for A squared came from squaring the eigenvalues of A. So it means that all the eigenvalues here of A squared must came from squaring eigenvalues from A. So it must be, in order to have 3 eigenvalues for a 3 to 3 matrix, it must be that A had 3 distinct eigenvalues. And therefore, the minimum polynomial of A can be divided into linear terms that each one of them to the power of 1, and therefore A is diagonalizable. So this was a long way to tell you that if the characteristic polynomial of A squared is indeed this one, so A is indeed diagonalizable, because we learned that all the eigenvalues of A squared came from squaring the eigenvalues of A, and we walked throughout the Jordan form of A, squared it, get a upper triangular matrix which is similar to A squared, and understood that the eigenvalues of this triangular matrix are square of the Jordan form of A. So, and remember that similarity preserve the eigenvalues of a matrix. So A squared is similar to a matrix that its eigenvalues are squared of the eigenvalues of A. So this was a long way to go, but I wish it was true and I had no mistakes in this. If there are, please tell me. And I think this is it. We did a little bit of the relationship between the eigenvalues of A and the eigenvalues of A squared, the characteristic polynomial of A, and the minimal polynomial, and a little bit played with eigenvalues and the relation between the eigenvalues of a and n squared. Thank you very much. If there are any mistakes or corrections, please tell me, and I think that this is it for now. Let's say goodbye for now.